Hello all, welcome to the third tutorial on simulation using Simscale platform. In this video, we are going to solve a structural problem. We are taking an angle bracket. You can say it as an angle bracket or an L clamp. The problem definition is it's an angle bracket which is supposed to carry maximum load of 150 kilogram. Then its horizontal member and vertical members are equal, and the maximum length will be 100 mm. Width of the L clamp is 25 mm. Then the material we are going to use is steel. The parameters, Young's modulus, yield strength are given here. Then we are supposed to fix this to the wall using two holes. Okay, so the diameter of the holes are given as 5 mm dia, and it should be countersink. Then the main objective is we want to optimize the weight, okay, with considering the strength and the rigidity of the L clamp. Hope you all are familiar with L clamps. The usual simple L clamp will be like this. Usually we are using these holes to fix on the wall, and these two holes should be fixed on a plate where we are going to keep our load. A modified version of an L clamp is like this. Okay, so there are different types of angle bracket we can use. So the first thing we want to do is we want to model this part. Okay, so for that we will use the on-shape platform. Okay, so we will first model a simple L clamp like this. I think you all are familiar with the on-shape. If you have any doubts, you can check with my previous videos on shape. I'll just show the dimensions here. We will take the front plane for drafting, sketching, and we'll make a sketch like this, 100 mm, and the thickness I arbitrarily taken as 10 mm. Okay, so 100, then I'll extrude and I'll get a L clamp like this. Okay, so this is one of the model. Then I'll use two hole features to put two holes. The whole dimensions also you can see here. Okay, so it is also you can see like this. We will first make the model. Then this is a simple L clamp. At the same time, I will make two more different models. Okay, so we'll compare these models according to the strength and rigidity of the parts. Okay, so for the second L clamp I used is like an L clamp like this. You can see we are giving a new one more member, a load sharing member, but the thickness we taken here we reduced. Okay, so from our experience, okay, so if you give a extra member, we can reduce the weight. Okay, so I took the thickness as 6 mm, 6 mm, 6 mm. The previous simple L clamp we take the thickness as 10 mm. Okay, so all the dimension you can see, and we made it like this, and then we again we need two holes also. And the third model which I took is a simple L clamp, but the section it's a C channel based L clamp, so the section will be a C section. Okay, so you can see here also the thickness which I took. You can see here we use loft to create this. The the loft trajectory will be like this. Then the sketch we taken is like this. Okay, you can note the dimension. Okay, so the sketch we taken is like this, and the width is a design constraint, 25 you cannot change, but the thickness you can change. Okay, so the thickness here we are giving is 4 mm. Okay, so so these three models I will first model in the on sheet, and we will consider this for the analysis purpose. Okay, so before going to the analysis, we can see the total volume of the components. Okay, so simply clicking this display mass property, and you can select this. You can see the volume is 28080 mm cube. Okay, so that is for the C-section L clamp. Then the supported L clamp, you can see the volume is 44992 mm cube, and for the simple L clamp, you can see it is 45992. So the main objective is to get a better strength with a less weight. Okay, so we are just considering the volume here because we are using the steel for all the L clamps. So if you compare the volume, you can directly compare the weight. Okay, so we already finished modeling. We will go to the Simscale platform. Okay, so first you can log into the Simscale, and the first thing we want to import the models from the on sheet. Okay, so first we will click on the import button. You can go to the corresponding project, and you can import the models. Okay, so simple L clamp we want to import, and supported L clamp we want to import, and the C-section L clamp we want to import. Okay, so these three models we will import. Okay, so all three models is already imported to the Simscale platform. So now the next step is we have now the geometry, so we want to move to the analysis. Okay, so before moving to the analysis, the first is the reprocessing steps, where we want to fix the type of the material, the boundary conditions all. Okay, so for that, what we want to do, we will first create a simulation for the simple L clamp. Okay, so simple L clamp, you can create the simulation. Click on the simple L clamp geometry, then you can select it's a static problem. Okay, it's a simple static problem. Create the simulation. Okay, so the simulation will be created. You can simply give the name for the simulation as a simple L clamp. Okay, so and tick. Then a simulation tree will be made, and you can go to each nodes in the tree to set the parameters. Okay, so the model we will have to set the gravity magnitude, and here you can see I'm going to make the loading from along the Z direction downward. Okay, so my weight will be acting downward, so I have to give here Z minus 1. Direction is equal to EZ minus 1, because my direction of loading will be in this Z. Okay, so you can I can check here also the coordinate system. The Z is in this direction. Okay, so then we will go for selecting the material. The material library will be loaded. You can just select steel. Okay, so apply, Then the material will be selected. You can see simple L clamp is selected, tick. Then you can go to the boundary conditions, click on the boundary conditions. So we are first giving a fixed support, that will be this portion, this portion, this portion and this portion. Okay, so that will be the fixed support. Click. So the fixed points we finished. Now we want to set up the surface load. Okay, so we actually 150 kilograms. Okay, so 150 kilograms, so we can convert it to Newton, that is 1500 Newton. Then the surface load we are applying as a surface load. Okay, so we want to calculate the surface load at this particular surface. For that, what we need the area of that surface. Okay, so that we can directly measure from the own shape. We can simply select the show measurement, click here and then click this area. Okay, so that will give you the area. Okay, so that area you select from there and then divide the total load with that surface area. It will give almost 0.7 into 10 raised to 6. Okay, so that is actually 0.7 megapascal for the surface area. Okay, so that surface load we want to, so we want to just select the surface load, then click on the surface, it will be get selected. Then our direction is very important. We are loading in the Z and downward. Okay, so we want to write minus 0.7. We can change the unit to megapascal. Okay, so our boundary conditions are finished. Our material is selected. That's enough for us to go ahead with the simulation. Okay, so all these nodes are now green. We can simply click to run the simulation and we can start the simulation. Okay, so you can start the simulation. Okay, so the simulation will go here. Okay, so it will go here. Okay, at the same time we can go ahead with the second simulation, that is for the supported L clamp. Click on there. You can start a create simulation, where you can click on the static. Same thing we will do, create simulation. Okay, so we'll write it as supported L clamp. That is the name we are giving for the simulation. Then we want to first set the gravity. Then we'll go to select the material, the same material we are selecting. See, in the background the other process is running. Okay, the simple L clamp, it is in the background, it is running. You don't worry about it. That time you can do another job. Okay, because the computational things are not doing inside your computer. It will be done on the Simscale server computers. Okay, it is actually processing in the cloud. Okay, so we don't worry about things. Okay, so we can concentrate on other problems. That time the you can see here 95% of the mesh for the first job is finished. Okay, after meshing it will go for the solving the equation. So the boundary condition, as we know, we are giving fixed support. Select this support, select this support, select this surface, okay. Then we'll go for the surface load. Click surface load, select the surface, give it as minus 0.7 megapascal. Okay, so that is finished. Meshing, you don't give anything, the meshing will be automatically doing. Okay, so at the same time we can do the second run. Okay, so it will be go. The second run mesh will be gone. So if you want to see the whether the first run is finished or not, you can simply go there and you can click on the run. Okay, so it is started, it is not finished, it is going on. Okay, so now the same time we'll go for the C section LCLAMP. You can do the same procedure here also. You can create a simulation, then select the static, then I can just give the gravity. You can define the gravity. Before that we'll give the name as C sec LCLAMP. Okay, so same way you can do that also. Okay, so I'm not waiting for the solution here because this problem is already done, so I can directly select it from the my previous results. Okay, so I'll just go there and I can see that results already. Okay, so these three I already made. Okay, so now we will go to the post processor. Okay, so you can see after the simulation, in the simulation window, in the simulation tree, you can see in the results simulation run, you can see the run, it is finished, and a post processor result button will be available there. Okay, so the finish and post processor button will be available there. Okay, so now we can view the result, post processor result. Click on that. You can see the first we will select the two important post-process parameters are the von-Mises stress and the displacement. Okay, so the von-Mises stress gives you whether the component is safe. Okay, it won't fail during the loading. Okay, so we will first check with the von-Mises stress. You can see a lot of red points are there, so better we will increase this toggle. Okay, so when you increase it to 250, you can see there is some values here, still red values are there. Okay, so we'll just make it as 250. You can see still there are red values. Okay, so we will see what is the actual value here. It is 345.2. Okay, so if you just click on the inspect point tool and click on the node, it is 345.2. Okay, so that means at this particular area the von-Mises stress is quite higher than the yield strength. The yield strength of the steel is approximately 250, so it is quite higher than the yield strength, and as per the von-Mises failure criterion, this won't succeed. Okay, so there is a stress concentration near the hole. Okay, so that will be about the von-Mises stress. So this design usually it is going to be a failure. Okay, so you have a stress concentration at that particular point. Okay, so we have to increase the thickness here. Okay, so that is the one way. As you increase the thickness, the weight will be increased. Okay, so we will now see, we'll check whether what would be the rigidity, the displacement magnitude. Okay, so the displacement, we can directly go to the displacement magnitude, and it is already in mm. It is 5.59 e raised to -1. So that will be 0.5. That is almost 0.5 mm. Okay, so 500 microns, almost 500 microns displacement is there. You can see it is not, the design is not rigid also. So if you want to see the animated deflection of this particular component, you can click here. You can add animations. Okay, so you can add the animations and just go to the displacement. I'll make it as a scaling factor, or just give a scaling factor of 10. Okay, so just give the scaling factor of 10, otherwise you cannot view this 0.5 mm displacement. Okay, so we want to scale it. For that, just make that scale point to 10, then select this as shape. Okay, then we don't need a full cycle, we just made it half. Okay, then you can just see how it is deflecting. Okay, so during the load, how it is deflecting. Okay, so you can see it is deflecting like this. Okay, so you can rotate and we can view at different angles how it is rotating. So as far as up to this point, this design is not satisfying. We will just check the next design. Okay, so we will go for the supported head clamp. Click on the supported head clamp. You can go to the simulation run and we'll just see the run. Okay, so that is also finished. You can see the post-processor result. Okay, so when we come to the post-processor results, see, first we will go to the on-Meisner stress. Okay, so on-Meisner stress, we will just make it as megapascal, and it's quite impressive readings you can have. Okay, so here 174.7 is the maximum stress. Okay, so that you can just click here and you can see the value. Okay, so if you click here, 141 is the Meisner stress at that point. Okay, so it's quite impressive compared to the last design. Okay, so simply by adding an extra component, even the thickness is less. Okay, so the first model, the thickness of the plate is 10 mm. Here we took only 6 mm plate. Okay, so we have an impressive results here. The yield point of the steel is 250. We know that it's quite less compared to the yield strength, the Meisner stress. So this is safe. And let's see about the displacement magnitude. You can simply click on the displacement, and it is 8.407 euros. So that is compared to the simple L clamp, it is quite less. Okay, so simple L clamp, it is almost 500 microns. Here it comes only 80 microns. Okay, so it is quite impressive. Okay, so that is a better design compared to the previous one. We will go to the next design also. We have one more design, that is C-section L clamps. Okay, we'll just check the C-section L clamp, what will be the results. Click on the simulation run and you can just click here, go to the post-processor results. Okay, so you can simply, first we will go to the Meisner stress. You can change to the value to megapascals. Okay, so here we have some problems. Okay, so it goes to, because the thickness we take here is 3.5 mm only. You can see here again you have stress concentrations. Okay, so here you have stress concentration. Here these 2 points are very weak points, but comparatively the other points are quite good. Okay, so if you want to check this point, you can simply click the inspect point, and it is 435.1, which is quite high compared to the yield strength. Okay, so this is not a good design, but if you want to see how the stress distribution is going on, we can use this channel for some modifications also for better design. Okay, so you can see as it comes down the range of 100, okay, that area is quite weak. Okay, so that area is quite weak. Definitely this is not a good design, but the weight, if you consider, this is almost 60% of the simple L clamp. Okay, so comparing these two things, that is the supported L clamp and C section L clamp, you can arrive at a new design. Okay, so with giving some rigidity as well as the strength. Okay, so we'll just go to the on shape and we'll make some modification with this. Okay, so we modified it with a channel design. Okay, so we made some channels and we modified the design. Okay, so now the main thing we observed in the supported L clamp is the stress intensity near the hole. Okay, so the stress distribution is not uniform near the hole. Stress concentration is there, it is a weak point, so we just give we increase the thickness at that point, and we made all the rust area, that is hole. Okay, so with a shell thickness of 2.5 mm. Okay, so and if you check the total weight, you can see it's 28,715 mm cube, which is comparatively very less to the simple L clamp, where it is almost 46,000 mm cube. Okay, so it is almost again 60%. So we modified it by getting the good design aspects from the C section as well as the supported L clamp. Okay, so now you can go ahead with the analysis and you can see how it is doing. Okay, so you can take this already we can import that model and you can do the analysis, and we'll just go through the result. Okay, so the simulation results, you can just click on the run and you can see the post processor. So it's quite impressive. You can see the Ohm's stress is just 85.19, that is the maximum Ohm's stress. Okay, so comparing to the supported L clamp, it is 149 maximum, and for the C section, even though the weight is quite less, for the C section, simple C section, it is the maximum is 450, in the range of 450 megapascal, and for the simple L clamp, it is in the range of 300. Okay, so compared to all the other three models, we modified the model, and you can see this is quite impressive. The stress distribution near the holes are now almost uniform, and if you come down in the toggle, you can see how the stress is distributed. Okay, so which are the weak points also you can see. Okay, so now if you move the Ohm's stress to 40 value, you can see the 40 areas. Okay, so like that, it is quite impressive. The design is quite impressive, and you can see the displacement also. We'll just go to the displacement magnitude. Okay, so now we change to the displacement, we change to mm. You can see it is 5.71 e raised to minus 2, that is 0.05 mm, that is 50 micron. Okay, so the displacement is also reduced, the deflection is also reduced. So compared to the C-section as well as the simple supported L clamp. You have more rigidity to this new design, as well as you reduce the weight also. Okay, so there are some more consideration you have to do about the manufacturing aspects. Whether you can manufacture it, that is a different thing. Okay, so that is a different perspective we want to analyze. So if you wish to see the displacement animation also, it is possible. Simply click on the displacement animation. We'll scale that to 25. Okay, so we'll here scale to 25 because the displacement is quite less. So we'll go, we select the shapes, then we'll just see how it is deflecting. Okay, so you can see the way it is deflecting. Okay, you can see the deflection. Okay, so how it is deflecting. It is scaled to 25. Okay, the actual deflection at this area is the maximum. There is red area 5.71 e raised to minus 2 mm is the total deflection. Okay, so by analyzing these 4 models, okay, so you can select this as the best. You consider the strength as well as the rigidity. Okay, so by this I am going to wind up this video, and thank you so much for watching. If you have any queries about this video, please post your questions under this video, and I'll make sure to answer you as soon as I can. See you in the next video. Thank you and bye bye.